So first, thanks for attending the talk. You've been listening to two privacy-related talks. Now we come to a relatively easy topic we call AI. Okay, so I would like to thank my collaborators, my students, and one of my collaborators actually here is the header of the Taiwan AI Research Center. So the story behind this AI security research is one day while we have random discussions, my student saying that we should do AI. I was like, why we should do AI? I said, everyone doing AI, so we have to do AI. But we are a cybersecurity lab, so how about we do AI cybersecurity? So with this said, quick outline. So this is one of the work we're moving towards the AI cybersecurity. Definitely have more topics to explore. So quickly outline. I will introduce the background, the key idea we called adversary example-based model stealing, and some case studies. So to save some time, I will not re-emphasize how important and how widely used the AI is. But the trend there is that first, AI, the deep neural network, one of the very typical AI implementation become more and more complex. And it's been widely used in certain area. We can still argue that AI is not secure, not that efficient, but we cannot deny that it's been widely used in certain areas. And the parameters also increase significantly. So from all the time, a few layers now with more than 10 layers with hundreds of millions of parameters. And in order to handle that, we kind of like looking into the cloud. So we do have DNN servers, but not every lab or every research kind of like institute can have that many. So people think about how about the cloud. In fact, all these cloud service, they provide something they call machine learning as a service. So this become our target that we try to look into how secure this service is. And so the brief process is that as a user, or we call the suppliers, you have a database of sensitive or secret or proprietary data. And the cloud is providing a training API. So you give the data to the training API in the cloud, and then you generate the model, and then the model becomes available to end users. So end user can query this model and pay some money to the original provider. So this is the very like typical machine learning as a service framework. So what we are looking into is first, the learned model is a black box. The original data is sensitive data. And the two goals for the cloud provider is that make sure that they provide a very rich prediction API and to protect the model confidentiality. So, okay, so this is all the background. And if you look into the cloud service, you can see that almost all the main cloud service provider have this service in. The only difference is that whether they allow you to customize it or not. So the majority of them, they allow you to customize that so that you can upload your own data set. And there are some special case for some specific applications. They don't allow you to customize it. They provide you that specific function already, so you can just use it in certain applications. Okay, so that's the background. As cybersecurity researchers, we are thinking about the security of that. So not just us. If you take a look at all the existing work, it's already there. People are already proposing that we can steal those models. So a few like typical paper listed there. But the main challenge here is still the parameters. So while all the work, well, I say old, it's a few years ago, they are looking into relatively simple DNN so that they can quickly recover the whole model. But recently, when we have hundreds of million parameters, so now we have the challenge that if we need to query this model for too many times, then the cost will be the hacking cost will be high. But if we try to query less times, then still the model's accuracy will be low. So far, we don't really see a good balance there. And one reason behind that is the way that how they steal the model is more or less like a random style model stealing. So that's exactly what we're trying to avoid. And while we are doing this, we are combining with another topic called adversary example. So how these two will be combined together? So adversary example, again, in this community, I don't need to re-emphasize what adversary example. I think half of you are working on similar topics. So you're just adding some perturbation, and so that the machine learning model would misclassify that, right? And we have all different kind of adverse example being proposed or developed. I raising two example. One is called non-feature-based. One is called feature-based. I mean, to be honest, they are not that much difference. But the key idea is that these days, adverse example can be so close to the original one. For example, this is the CW case. The original image and the malicious image, you can see that the raw eye can hardly tell the difference. And this is the feature adversary attack. You have the source image, you have the target image, and you have this perturbation. The adversary example is so close to our human raw eyes to the original one. So let's take a deeper look at the adversary example and to see why this will link to our model stealing attack. So you have a source example, or we saw the source image, or whatever the source original object it is. Then what's the next step is that you want to generate adversary example. And there is a hidden line here. This line is a hypothetical boundary. Within this boundary, the AI can still, the deep neural network can still classify it correctly. Outside the boundary, the AI would misclassify that. So what we do is that we are trying to generating a lot of perturbation to see where this image will be located. And we realize that we will generate in total, like we called 6 of them. What are they? The original image, we have we called kind of like a medium confidence, low confidence. These images are still being classified correctly. But in the same time, we will generate malicious examples. On this side, they are all malicious examples. These are like a low confidence, medium confidence, high confidence. So here, as an adversary example, while we are working on that, our objective is to generate as many as those red triangle examples so that they are both high confidence and malicious, right? But in order to steal this boundary, we realize that, in fact, the best of this example to help us identify the boundary is those we call the low or minimum confidence data. Because they are minimum confidence, they are very close to the boundary. So instead of using all this data, to help us identify the boundary, we can simply using the data or generate as many data as we can around the boundary with a very minimum confidence. They could be classified around or be classified correctly. And apply on this data, it can help us sufficiently and efficiently identify the boundary. And eventually, what our job is that to identify the whole boundary so that reproduce the model in the cloud. Okay, so this is one key idea. And in order to do that, because none of the previous adverse example have this as a target, even though, as I will show you later, any adverse example can be repurposed to this goal. And what we do is that we're developing another adversary example we call featureful, which is a margin-based adversary example generation algorithm. So the key idea is that instead of generating the high confidence adversary example, we're trying to generate very low confidence adversary or non-adversary example as our like stealing training set. So this is the equation, and this is the key idea that you have the source image, you have adversary perturbation, you have the target image, and you keep on doing the feedback loop. You're trying to see that if you certain perturbation will generate too high confidence, then we will try to lower the confidence. If it become too low, the lower the better, right? So this is the key thing. So for example, like this is the image this is a typical featureful generated image. From among all these three figures, the leftmost column is showing you the original image. The middle one is the guided or the target image, and the right one is adversary or non-adversary example. So what you would see that for the left column, we correctly identify them with high confidence. For the middle one, it's also being correctly identified, but for the right one, it's a malicious example, but the confidence is very low, which means that even though the AI or the DNN network, they think it's happy, but it tells you that I'm not very confident. In general adversary example, we will discard those images because they are not the goal we want to generate. But in our case, we need those images because it tells us that these images are very close to that boundary. Okay, so with this as the basic idea, so then we go through the whole process of the model stealing attack. So we have the adversary, and we have the cloud, which we don't really know as a black box. And we're using all these low confidence adversary example or non-adversary example to query this one and to generate the results from the cloud to see whether it's close to the boundary. And then using the result, we retrain a local module. As I mentioned earlier, a cloud module, a cloud DN framework normally have hundreds of millions of parameters. Our goal is not to recover precisely all these hundreds of millions parameters. Our goal is just to generate a local model which have totally different parameters, but have the exact same classification scale. So on this way, we going a bit further. We have the source image, which is a regular image. We also have the problem domain, which we call the adversary example. And we put them into the database, and we generate data set, and we retrain a local module. The local module, we actually do some trick here. So the local module is that we have a few layers. Some of the layer is a fixed layer, some of the layer is adjusted layer. Because we know that given this small set of the example is not sufficient to train the whole DNN from the beginning. In fact, that's not our goal. So what we do is that we just find a local substitution model and switching a few layers on that. Switching a few layers, our data should be sufficient. And then get the prediction result. And here with another interesting challenge we try to solve is that how you pick the local module. Because we say that if we want to steal the model in the cloud, we need to have a local module. And our result proves that any local module should work. So that's an interesting part. We want to look into further, like why DN model can be kind of like this transfer learning style, why it would work theoretically. But our finding is that any of the complex local substitute models should work. But among all of them, for example, if we try to steal the emotion classification cloud module, we can choose all the different local modules. But among all of them, the best performance is achieved by VGG face. So it kind of tells us that if you trying to steal a model in the cloud, you'd better have the substitutory module which doing a similar task. For the emotion classification, then you're using VGG face, but you can use any other one, LXNet, VGG19, ResNet, they all work. They all can achieve good result, but it's just the VGG face would achieve the best one. Okay, so I think after that, we just tell you some result. So this is, we're using, in the paper we have more result, but in this one we have the Microsoft, the traffic and the flower classification. And we can see that with very few, like around like 2,000 query, we can achieve almost the same accuracy with this original cloud. And again, as I said, feature 4 is just one of them. We can repurpose all the existing, this is a random selection, this is not a consideration, but the PGD, the CW, the FA, the feature adversary, we can repurpose all existing adversary example to make them generating us the boundary minimum example. So feature 4 is just one example dedicated for this one, but other thing, in fact, we realized that CW actually in some times achieve even better performance than our tool. But the CW original goal is not for this, so we have to repurpose the design. Okay, so again, as a comparison, you can see that our is one of the first to balance that we need very few query to steal these hundreds of millions of parameter models from the cloud. And very quickly, I go through the defense. The defense, so far, they are not a very efficient defense there. The one typical one is called the Prada defense. And we can see that if we repurpose all this design, we can easily evade that. But Prada is trying to identify the spreading, the distribution of all the image you are trying to query. If you always query this kind of like closure boundary, they may identify that. But it can be easily like evaded. So, okay, given time constraint, quickly, so I want to say that we are the first, or one of the first in AI area. No one can always claim they are the first to do something. While the paper being published here, I assume that the similar paper may be published in other AI venues. So, but the idea here is that we identify one of the like large-scale DNN model stealing method. And relying on very small finding we have is that those low confidence model, which is across the boundary, will be very helpful in stealing the models. We definitely need to dig more to figure out what is the theoretical background there and to understand more on the adversary example and model stealing. With that said, I thank you for your attention. All right.
Cool. So we have time for perhaps 1 or 2 questions. Please say your name, your affiliation.
Shan from University of Chicago. Really interesting work. I have like 2 questions.
Yes.
So the first one is that I think you evaluate some just normal models, like non-robust models, as you upload data, train, and normally the services are not robust, but in realistic, the online services are normally have really extremely robust model, and it seems their decision boundaries will be harder to prune and harder to learn. Do you guys evaluate something like that?
So very good point. So in fact, this is something I hope my click can fast enough to go to those examples. So we have, I think I mentioned this for some of the model which it's black box to us, not customizable. So in the image here, so I wish I could have the, okay, here we go. Here we go. So for some of the model, yes, they allow us to customize it, so we uploaded the image. But for some of others, we are not allowed to change that. For those, in fact, we don't even know what their source image, how they change that. We contact the cloud service, but they won't share us any information. So we assume that these are more robust, and our attack achieved a similar goal there.
I see.
Yeah.
And the second question is that I think you guys reduced the number of queries to the service, but there seems to be like two factors to impact that. One is using transfer learning, and another is using the adversarial sample.
Yes.
And do you guys separate those two impacts? Like, for example, only measure using transfer learning with some of the previous work, and another way around as well.
Very good. We do separate them. I think we need to figure out, because using either of them can also achieve relatively good results. But the combined result is not like double the like steel effect. So that's actually a very good point. We may need to dig further. Yes.
Saurabh Bakshi from Purdue. So your machine learning as a service is responding to the queries with a confidence value, correct?
Yes.
So how robust is the attack if the confidence value is not revealed by the service, or if it is perturbed by the service?
So so far, because of this, we have two parts, transfer learning and adverse example part. So if we don't have the confidence value, which means that the adverse example part will be much weaker than what we present here, as I just answered the first question. So the outcome is not like significantly worse than we have here. It's still like achieve that level, maybe from like 80% to 60–70%. But we still not know why it's like this is something that we want to dig further, like only using one of them can already achieve that level of confidence, but not more. Yes, very good question.
All right, let's thank the speaker one more time.